Since most of us are preparing for entrance exams, let's take a real entrance exam kind of question. Suppose you have a test which consists of 20 questions, out of which you have 10 verbal questions and 10 quant questions, and there are a few conditions to do well in the test. You need to attempt a minimum of 2 verbal questions and you need to attempt a minimum of 3 quant questions. It is given to you that every verbal question can be attempted in 4 minutes and every quant question can be attempted in 6 minutes. Now, if all these conditions are to be satisfied and if the total time that is available to you is 36 minutes, then in how many ways can this test be attempted? If you're wondering how this can actually be an introduction to graphs, because I'm assuming most of you would be thinking of using equations or inequations to solve this question, let's go through a few concepts of graphs, and then when we come back after going through the concepts, you will understand how we can solve this question in a very simple manner using graphs. Let's look at graphs of some standard functions. Let's start off with a very basic function which is called as identity function. Identity function basically says fx is equal to x. So y, which is equal to fx, is equal to x. Now if we try to draw the graph of this particular identity function, and if we try to just look at what happens in terms of values, when x is 1, y is 1, when x is 2, y is 2, if x is minus 3, y is minus 3, and so on. So if we try to plot this on a graph, this graph would be a straight line passing through the origin, and it would be such that the angle of this line with respect to the x-axis would be 45 degrees, because only then will you get the values as equal. At x is equal to 1, y also has to be 1, at x equal to 2, y has to be 2, and so on. So this particular line that we've drawn as a graph is the graph for an identity function, which is fx is equal to x. Let's look at some other function. Let's assume we are looking at a constant function where y as a function of x is equal to some constant k. Now depending on the value of k, if we say that the value of k is 2, then what this means is whatever be the value of x, the value of y will always be 2. And hence if we try to draw this as a graph, at y equal to 2, we will get a horizontal line which is a line parallel to the x-axis. So this graph actually tells us that irrespective of what the value of x is, the value of y always remains constant, which is equal to 2. So in this first case, we've looked at two functions: identity function, which is a line passing through the origin at 45 degrees angle, and a constant function, which is nothing but a line parallel to the x-axis. Let's look at another type of function which is known as absolute value function or modulus function. Suppose we say y as a function of x is equal to mod of x. Now a characteristic of an absolute value function is that whether x is positive or negative, y will always be positive. If x is 0, then y will be 0, and hence we can say that the absolute value function will always give us a value which is non-negative. Since the value of y is always going to be non-negative, we can safely say that the absolute value function will maybe originate from the x-axis and will be above the x-axis. Once again, if we start putting in values, if x is 1, y is 1, if x is 2, y is 2, and so on, if we plot this as a graph, we are going to get this part for all positive values of x originating from this point O when x is 0, and when we look at negative values of x, the value of y would still be positive, and hence this is the kind of graph that we would get for the absolute value function. Another way of understanding this is based on something that we've already seen in the chapter of functions earlier, where we have seen that when we look at absolute value, then absolute value refers to distance from the origin. So when we say mod of x, it is distance from the origin, and as the distance goes on increasing, the value of y, which actually is calculated as mod x, also goes on increasing. So this is how our absolute value function would look in terms of a graph. Now instead of mod of x, if we had said y as a function of x is mod of x minus 2. Now when we had mod of x, it meant distance from the origin, and here when we say mod of x minus 2, it is the distance from x equal to 2, and hence the graph will now originate from this point x equal to 2 and then would be similar to what we have drawn earlier, except that the base point of the graph would be at this point x equal to 2. So this is what a modulus or an absolute value function would look like graphically. The next function that we would look at is called as the integer value function. Now in integer value function, we would look at two different types of integer value functions. One which is known as the greatest integer value function, and the other which is known as the least integer value function. The way the greatest integer value function is denoted, y as a function of x, is represented in terms of the rectangular bracket or the box bracket within which there is x. The way the greatest integer value function value is actually arrived at, it is the largest integer less than or equal to the given x value. And hence if we are, let's say, looking at something like 2.7, then we look at the largest integer which is less than or equal to 2.7, and hence when we look at the largest integer less than 2.7, it would be 2. Similarly, if we are looking at, let's say, the largest integer or the greatest integer function value for minus 2.7, then it would be the greatest integer less than minus 2.7, which is minus 3. If we were to plot this in terms of a graph, when x is 0, the value of y is going to be 0, and until x becomes 1, for every value, let's say 0.1, 0.2, 0.3, whatever value we consider, the value of y, when we are looking at the greatest integer value function, it would remain as 0 itself, and hence for all values up to x equal to 1, the graph would coincide with the x-axis. The moment x becomes 1, the value of y would also become 1, and then the value of y would stay at 1 itself till the value of x becomes 2. The moment x becomes 2, the value of y would become 2 and it would stay there till x becomes 3, and so on, and hence this is the kind of graph that we would get for positive values of x. Let's now look at what happens for negative values of x. If the value of x is minus 0.5, then the value of y for that would be minus 1, because we are looking at the greatest integer less than minus 0.5. So if we just eliminate this O here so that the graph becomes visible, for all negative values of x, the value of y would be minus 1. If I go on to values between minus 1 and minus 2, then the value of y would be minus 2, and this is the kind of graph that we would get for the greatest integer function value. Let's look at the other type of integer value function, which is the least integer value function, which is represented as the round bracket within which there is x. And if we were to calculate for these same values the least integer function value is given as the least integer greater than or equal to the given value of x. So if I want to find this, then I am looking at the least integer greater than 2.7, which would be 3, and here the least integer which would be greater than minus 2.7 would be actually minus 2. If I now start plotting the least integer function graph, for all values greater than 0 and up to 1, the least integer function value would be 1, and hence we would get the graph as this at y equal to 1. The moment the value of x crosses 1, and even if it becomes 1.05, let's assume, the value of y would automatically become 2 because it's the least integer greater than the given value, and we move on in this manner. If I move to the negative side, so for example, anything when x is 0, y would stay 0. If x is minus 0.5, then the value of y would become 0. So this part of the x-axis would actually be your least integer function graph, and so on. So effectively, if we compare the greatest and the least integer function graphs for a certain value of x, the least integer function graph would always be one step above the greatest integer function graph. In fact, the way this entire graph looks, this kind of a function is also known as the step function. And looking at this, we can safely conclude that least integer function graph is one step above the greatest integer function graph for the same value of x. So what you can see right now is actually the solution to the problem we had discussed initially. Just to recap, we were looking at a test consisting of 10 verbal and 10 quant questions. We have to solve a minimum of 2 verbal questions and a minimum of 3 quant questions. The time required to solve a verbal question is 4 minutes, and the time required to solve a quant question is 6 minutes, and the maximum possible time available is 36 minutes. And the question asked was, in how many ways can such a test be attempted? So if you look at this graph now, and if we say that this horizontal x-axis refers to the number of quant questions that can be attempted, and if you look at this vertical line which is drawn at x equal to 3, since we were given that we need to attempt a minimum of 3 quant questions, which means q has to be greater than or equal to 3, and hence we are looking at this area on the right hand side of this vertical line at x equal to 3. We were also told that number of verbal questions is minimum 2 if this y-axis represents the number of verbal questions, and we've drawn this blue line at y equal to 2. So we are now talking about this area which is above this blue line, and we were also given information that to solve a verbal question it takes 4 minutes, and to solve a quant question it takes 6 minutes. So we say 4v plus 6q should be less than or equal to 36 because the test needs to be attempted in a maximum of 36 minutes. This line is actually represented by this red line, and now it says that it should be less than or equal to, and hence we are looking at this area below the red line, which essentially means that the common area is nothing but this triangle that has been formed out here. And if you look at the question asked, in how many ways can such a test be attempted, we are looking at all possible integer solutions in this common triangle area, which basically means this is an integer point, this is an integer point, there is an integer point here, here, this one and this one. And hence if you look at the number of crosses, there are 7 possible crosses, and hence the answer is that there are 7 ways in which such a test can be attempted. I don't know how many of us initially thought that such a question can be solved using graphs, but the beauty of graphs is the moment you do a graph or you make a graph, and then when you look at it, the entire visual element gives a very clear idea of how the question needs to be solved, and hence whenever a question can be solved in this visual manner, it is maybe a foolproof or a very quick way of solving a question. This is how this question can be done in a graphical manner.